Welcome to Aerospace Testing International and North Star Imaging's webinar on the role of computed tomography in accelerating the development and qualification of additively manufactured processes and products. Our speaker today is Brett Muehlhauser, a leading expert in the field of CT scanning and digital radiography and a research and development technical fellow at NSI. Brett's been with NSI for 20 years, and as well as R&D, he writes and teaches NSI training courses. He's worked in digital radiography for more than 30 years and also worked in the aerospace industry for 15 years, doing product development, product evaluations, and failure analysis. Brett is an ASNT and NAS 410 Level 3. I know this presentation will be interesting and informative for you. One small thing first though, please. There will be a short Q&A session after the presentation. If you have any questions, please post them in the Ask a Question box you should have on your screens. So, thanks for attending everyone, and over to you, Brett.
For those of you that may not be as familiar with North Star Imaging, we've been in business for 34 years, and we are a leading provider of industrial CT and DR X-ray systems. Our headquarters are in Rogers, Minnesota, where the X-ray systems are manufactured. We have 5 other facilities worldwide: Los Angeles, California, Marlborough, Massachusetts, Paris, France, United Kingdom, and Suzhou, China. Each facility is equipped with multiple X-ray systems performing application studies and inspection services for our customers in each of the labs. NSI is an ITW company, and in this industry you may recognize the names of a few of our sister companies such as Buehler, Instron, and Magnaflux. Some exciting news about our California facility. We have outgrown the existing facility in the LA area, and we're moving just down the road a bit to a much larger facility that will be up and operational June 1st. Along with that move, we are now completing the build of a world-class high-energy lab. It will be equipped with a dual 3.5 and 6 MeV Linetron system from Varex. The system will be able to handle really large parts with a weight capacity up to 2,000 pounds. The vault is already built and the equipment begins installation within a week or two. So obviously this will be a really valuable tool for CT scanning some of the heavier alloy AM parts. This slide was meant to provide a quick review of the basics of cone beam CT. So on the left is the X-ray tube projecting a cone of radiation toward the flat panel detector on the right. The sample is placed on a precision rotational stage in between the tube and the detector, and a single digital radiograph is produced as the image of the part is projected onto the detector. The sample is then rotated for typically 360 degrees, while the image acquisition process is repeated, capturing a full set of radiographs throughout the rotation. The acquired data is then reconstructed directly into a volume for visualization. We can then export 2D slices from the volume, surface the volume, perform advanced visualization and metrology. NSI software is used for the acquisition, the reconstruction, and the visualization of the CT data. When we look at the applications of CT in materials and manufacturing, most of us are familiar with the use of CT for part inspection. We're looking for internal integrity of products. There's, however, a lot of applications where metrology is being performed using CT, where we're looking for internal and external dimensions of a part. Reverse engineering, finite element analysis, many applications for CT in that arena, as well as the AM 3D printing that we're going to be showing. This really applies across all material sectors, so metals, ceramics, composites, polymers, and foams. So you'll see pretty much all materials represented. When you look at how rapidly additive manufacturing is being applied across all industry sectors, it really speaks to the strength of the technology. In our inspection service labs, we perform more CT scans on AM parts than from any other single manufacturing method. I'll skim over this slide fairly quickly, but overall, during the presentation, we're going to be discussing different applications of CT in the additive manufacturing processes. So part of that will be looking at design and product improvements and optimizations, even including design simulation processes and how we can use CT to further improve that. further improve the in situ monitoring process, how we can use CT to evaluate the hipping process. So by CT scanning a part prior to hipping and then after hipping, taking a look at what that impact is from the hipping process itself, and then discuss some of the process control checks, reverse engineering, different inspection steps, and the metrology. There's a significant advantage in performing FE simulations of AM product designs. However, one of the missing components is when I hit print, how does the end result part really compare in dimension, internal integrity, and material properties? CT can be used to provide an as-built model of the part that can be compared to the as-designed model. Once we've scanned the as-built sample, we can take that 3D image data, place it into Simpleware, and then use that in the FE model. So basically, we leverage Simpleware to reconstruct the as-built geometry with a real fine mesh structure. This slide is just an example of the high detail surface mesh data that can be generated by the Simpleware software. By CT scanning the as-built sample, we can compare the printed part to the original CAD to compare any geometric deviations from the design. We can then enter that as-built data back into the finite element simulation model to see what the impact will be. When we compare the FE simulation results from the image-based model to that of the CAD-based model, we can see that the max deformation and the max principal stress results were well within the acceptable range. So that shows that the CAD-based model wasn't too far off from the actual printed part, but this allows us to provide an improved FE model for the printed parts going forward. Some of the process considerations that can impact CT are the types of defects that occur for a given AM method and material. For example, unfused powder in the laser powder bed process compared to lack of fusion type defects using the direct energy deposition process. The location and the orientation of defects are also factors to consider, and the material density and thickness of a part can also have an impact on image quality. By introducing known defects into test coupons, we can verify the detectability with CT and then perform mechanical testing on the coupons. This NavAir provided image of an unfused powder defect is a great example of this. These are all really good reasons to make use of known defect standards for qualifying both the AM and CT processes. Here's a great set of images from NavAir where they designed and printed a specific size and orientation of unfused powder defects into coupons. They then verified the detectability of the defects with CT prior to performing mechanical testing. And obviously, this data can be really useful in FE models. In situ monitoring technology continues to make advancements in numerous AM processes. A great way to initially evaluate and then improve upon the effectiveness of the process is by understanding the correlation between the in situ monitoring of the AM part and the results from a CT scan of the part. Layer by layer data from in situ detectors can be spatially correlated to CT scan data to provide tweaking of the process to improve prediction models of discontinuities forming. Basically, if in situ monitoring of the melt pool predicts a porosity of a specific size is likely to occur at a given location within the build, there should be a direct correlation for that indication within the CT scan. Once this correlation has been optimized, CT can be used to validate final in situ programs and used to perform process control monitoring over time. These images represent a small sample of the extensive work NavAir has performed in the qualification of AM parts for aircraft over the years. NavAir has statutory authority for airworthiness approval for Navy and Marine Corps aircraft, so basically equivalent of FAA certification for civilian aircraft. When you look at this product build, you can see there's a substantial amount of coupons that are part of the build. NavAir has done extensive testing to answer the questions on this slide, such as what is the correlation between the bars or coupons and the parts as it relates to material defects and material properties, and our part coupons also required to validate that correlation. Additionally, it needs to be understood if the correlation is consistent across build locations and from one build to the next. To help with that correlation, all the bars, the coupons, and the parts can be CT scanned prior to material testing. For example, you don't want to have material properties from a clean tensile bar represent a part that's filled with microporosity. On this slide, we show a DR image on the top and a CT slice on the bottom. So the DR image on the top was actually one of many of the images that was used to generate the CT slice on the bottom. However, the microporosity that we see on the bottom, on the order of 40 micron in size, or roughly 1.5 thou, are not even visible in the DR image, even though the DR image was one of them used to generate that slice information. And basically what's going on is we have all of this superimposed information, and the thicker the part, the more superimposed information you have, so the more difficult it is to be able to generate the contrast sensitivity that you see in the bottom slice. With the DR data, you can do 2D measurements. The CT data, we can slice through the part back and forth in a direction and then be able to generate volumetric data as well as 2D and 3D metrology. In DR and CT, the thicker the part, the less contrast sensitivity you have for smaller indications. Here's just a few examples of parts having complex geometries. So one of the cool things about additive manufacturing, of course, is the complexity of the parts that we can make. With that, however, comes more difficulties for the standard radiography methods. So when you have multiple superimposed features or rough surfaces, and maybe even combined with lattice structures like the sample on the left, the probability of detection can drop significantly with standard digital radiography, but this is where CT really shines. Also, if you look at performing metrology on these types of parts, measurements of many of the internal features are often not even possible without CT. The following few slides will provide examples of AM products being evaluated at NASA Goddard Space Flight Center using an NSI CT system. The first sample here is an AM cylinder that's being evaluated, and there's a fabrication crack that breaks the surface, and it's clearly visible with CT. However, it's not visible even under a microscope due to the inherent surface roughness from the AM fab. There's also microporosity that's visible in a specific slice area in close proximity to the crack. This sample was part of a cylinder crack study at NASA where samples were intentionally cracked to varying degrees of depth. The surface roughness and the internal microstructure was also varied with the goal of better understanding the impact of those process changes on the other NDE detectability of the varying degrees of cracking. CT was used to characterize the cracking within the samples. An inverted surface visualization function was performed to display the crack formation in the two images on the right. This NASA concept part was built to evaluate the possibility of replacing a product that was being fabricated using a complex series of braze joints. The wall structure and thickness in the right image was being evaluated using CT. This is a pretty cool sample we scanned from the Navajo Tech Center for Digital Technologies. One of the students there developed a lattice structure design that is based on the Navajo rug weave design. We were able to clearly evaluate the full structure using CT, and they now use one of our X3000 CT systems at their facility to evaluate samples from their various AM technologies. This is a great example where CT can be used not only for evaluating the internal integrity of a part, but also for reverse engineering. So on the left-hand side, we see a surfaced volume of a CT scan of this plastic injection molded part. And it's real obvious that there's a substantial amount of void showing up here. When we put this semi-transparent viewing to this surface, you can rotate the volume around as if it's a transparent part that you can just see inside to be able to inspect. In the middle, you can see these large and small voids. So we're really evaluating to identify whether or not there's any leak path that currently is occurring or something that's near close to the surface that could generate a leak path in the future. And then on the right-hand side, we have a printed part. So basically, we took the CT data and we generated an STL from that, cleaned up the STL to remove those voids, otherwise you print those also, and then we ended up with this printed part on the right-hand side with great structure and no voids. This is a great example where CT can be applied to reverse engineering. In this case, NavAir has aluminum castings that were legacy parts that didn't have any CAD models associated with them. So we could do a CT scan, generate a surface from that, a CAD model, an STL file that we can send to an AM build. Once the part is built, then we can do a CT analysis of the part, as well as create a file that we can plug back into an FEA model, and if necessary, understand where we may need to beef up the part relative to the AM build material properties compared to the casting properties. And then obviously the part goes through the normal qualification testing and material properties testing from coupons, etc. Here's another successful NavAir legacy part build using additive manufacturing. On the left is a CT scan of the legacy casting displaying multiple porosities, and on the right is a very solid AM part having no visible discontinuities. A critical component in the use of CT is the qualification of the CT system and technique for a given application. The easiest way to do this is through the use of representative quality indicators, or RQIs. These RQIs need to be able to adequately represent the product being imaged and the types of defects that could occur within the build process. One of the simplest ways to do this is to print 3 actual parts or representative parts. One part would be built without any known defects, and the other 2 parts having known defects equal to or smaller than the minimum rejectable size. When we CT scan the 3 parts, 2 of the parts should be able to display all the known defects, while the good part should not have any rejectable discontinuities. One of the 2 defective parts should be cross-sectioned to validate the CT findings and confirm the size of the actual printed defects, and that other defects are not present that are missed by CT. The other can be used for performing process control checks on a daily or weekly basis. And once the confidence is gained in the full detectability through CT for similar applications, it may be possible to eliminate the cross-sectioning of the second part. Another way to build RQIs for the qualification of the CT system and technique is to either print or machine defect inserts that can be placed within a part or representative part. The placement orientation of planar defects is critical, and the build plane for the product should be considered. The defects can be either left empty or filled with representative powder or inclusion material. The benefits of the 2-part disc approach is that the RQI's features can be dimensionally verified with conventional methods. These CT images represent some of the types of RQI inserts that we use to better understand the detectability of different shapes, sizes, and positions of unfused powder defects in Inconel 718 material in this case. The inserts are designed to be placed into parts or representative parts in locations that typically represent the worst case location for detectability. Even though some of the feature sizes are large, they can still be very useful in representing, for example, trapped powder within a part. The 2 inserts on the left can be configured to provide one chamber powder filled and the other chamber empty for comparison. The planar defect configurations on the right would represent larger diameter unfused powder defects with varying thicknesses and orientation. The varying size features allow for these inserts to be placed within really thick materials for high energy imaging also. This slide displays the STL dimensions of the RQI insert for the spherical unfused powder defects. The sizes range from 2 mm down to 0.2 mm. The 5 larger indications are clearly visible in the image, but the 0.2 mm indication is only visible with further digital magnification and contrast enhancement. Based on the non-spherical shape of some of the other indications and the undersized measurement of the 0.2 indication, it appears that the print resolution was likely not able to accurately print the 0.2 mm spherical void. This is a CT slice of the RQI insert at the 500 micron defect position. We can clearly see that the defect is not fully spherical, and there is a section in the center that is approximately 120 micron in size that is likely fused powder. Subpixel imaging is an NSI innovation that is used for both DR and CT. Overall, during the imaging, the product stays stationary and the detector moves a specified subpixel distance. So you take a single pixel and divide it to 2 by 2 or 4 images, 3 by 3, 9 images. So overall, this provides a higher resolution imaging for a given detector pixel pitch. This is especially important when we're talking about using high energy systems with larger focal spots and lower geometric magnification, such as with a mini focus X-ray or a linear accelerator. The lower magnification provides for larger field of view for a given resolution, and these larger focal spot tubes can produce higher photon counts, allowing higher frame rates for faster acquisition, which can help balance the time in acquiring the additional subpixel images. Subpix is also used extensively to push image resolution even higher with microfocus tubes and geometric magnification. Here's another example of a standard and subpix scan comparison. This sample is an additive manufactured part. On the left-hand side, we generated a technique that provided a 44 micron voxel size, and you can just start to begin to see the porosity showing up next to the red arrows. On the right-hand side, we generated a subpix technique. All other processing variables, again, the same, except for the movement of the detector, creating 4 images in a subpix mode. And we ended up with a 22 micron voxel size. And you can clearly see the porosity showing up now. The technique for this subpix scan of a printed metal part generated a 15 micron voxel size, which revealed multiple porosity toward the edge of the part, the smallest being approximately 42 microns. When we scanned one of our RQIs with the 2 different techniques, the 200 and the 400 micron powder field indications were visible with both the standard and the subpix scan techniques. However, the subpix displayed more detail about the indication. In a production environment, it's always a balancing act between spatial resolution and field of view. Subpix can provide either a higher spatial resolution for a given field of view or an equal spatial resolution for a larger field of view. In this slide, we look at some of the advantages of CT over traditional measurement methods. The most obvious advantage is that with CT, we can perform internal dimensions on even fully closed chambers within a part while also capturing all of the external features. For a lot of parts, this often provides the opportunity to inspect the product for internal integrity while also retrieving the required metrology data from a single CT scan. This can often remove the requirement for cross-sectioning parts for first article inspections. CT can also be used to help improve or even validate some of the in situ geometry systems that capture layer by layer geometry during an AM build. CT metrology standards are being developed by numerous organizations worldwide, such as VDI/VDE, ISO 10360, ASTM, and ASME B89. With that said, CT metrology has been applied effectively for over a decade in some major aerospace companies using their own company-specific procedures. Another aspect of CT metrology is the idea of being able to measure discontinuities 3-dimensionally. This provides the opportunity for applying 3-dimensional acceptance criteria. And when you look at the product development process today, we design in 3D, we do FEA in 3D, we now print parts in 3D. It only makes sense that we start inspecting product to 3D criteria. With all the CT scanning we do at NSI, the majority of it is data that we can't share. So we're very grateful to these folks for letting us use some of their work and cool CT scan data in this presentation. We want to give a special thanks to Dr. Justin Jones from NASA Goddard, Dr. Brandy Briggs and Dr. Jay Wetterman from NavAir, Scott Halliday from Navajo Technical University, and Dr. Karim Jentz from Synopsys. Thank you all. Well, I thank you all for your time. I appreciate you attending.